and it's getting ready to live stream now. And here we go. These couple of slides here should hopefully only take about a couple of minutes to show. Kai could not make it today. Kai Ceviak, KE4PT. He's a QST contributing editor and editor of QEX magazine, and that's what this little slideshow is about. And hopefully it will now take me back to that, I hope. There we go. And I think we're now on YouTube. Okay, so welcome back to our afternoon session here. We're now streaming on YouTube. I'm presenting this on behalf of Kai Ceviak, KE4PT, Kilo Echo 4 Papa Tango, the contributing editor to QST magazine and editor for QEX. And he asked you to write for QEX and QST. These, by the way, these slides are on the section website under the TECHCON presentations. You may download them. By the way, in case you do not know, since January of 2000, or I think about March or April of last year, all digital editions of all 4 magazines are now part of your membership benefit. I think it's the greatest membership benefit to that the league has added in many years. So you can see QST, QEX, National Contest Journal, and the new On the Air magazine. Now, all 4 digital editions are posted. I personally order the periodicals DVD every year. As a matter of fact, my shipment got hung up in the storm up north, and I'm still waiting on it. It's now showing in Tennessee, so I hope to have it maybe early next week. But I still like the digital editions because I can carry them on my Android tablet or look at them on the computer and all the stuff that's not in the print versions. So that's now a standard membership benefit. So take advantage of that if you're not already doing so. And Kai is looking for articles, short technical notes, and it does pay. The best thing, you get paid to be an author. Detailed technical articles. And now that QEX has a tremendously wider audience since last year, since they now have the digital edition online. And consider QST magazine. You say, I've never written before. That's okay. There's always a first time. I wrote for an article back in 2016 with a Fpga based ID timer. I got the inspiration from someone who built a 555 timer to remind them when to ID. So I built up a version using the Fpga microcontroller. And I've done presentations at previous TechCons here on the introduction to the Fpga. Help get Mike, one of our speaker 2 o'clock, started on it. But consider writing for QEX or QST. You do get paid for it. It's $65 a printed page in QST and $50 in QEX. Why the price difference? I don't know, but that's what it is. And there's the contact information you see for Kai. And again, that you can download this presentation. It'll have the links to it and everything. Becky Schoenfeld does an excellent job as the QST's editorial director. I believe she may be taking over for Steve Ford, who's going to be retiring soon. I think she may be going to be in that position by now. But Kai is the one that runs, and he lives in Broward County, so he's actually over in the Southern Florida section. And thank you for your support. And that is that presentation. All right, well, Scotty, you can bring yours up at this time. He's gonna. This was one that I asked Scotty to do. I was quite fascinated when I saw this at the ARRL Tapper Digital Communications Conference, and so I asked Scotty if he'd be willing to do this. And so, Scotty, I'm going to let you take it away, and I will mute everyone except yourself. And you should hopefully be on. If not, I will unmute you. You may go ahead and start.
Can you see the screen okay, Daryl?
Yes, sir.
Okay.
Yes, sir. It's on, and your presentation's up.
All right. Thank you very much, Daryl, and thanks for inviting me to make this talk. I know it's a little bit tend to get overwhelmed with requests for articles and talks when you're building something new, but it's something we have to do because we want all of you guys to hear about it and hopefully be half as excited as I am about a new piece of hardware that's coming out. So at any rate, I hope some of you have maybe seen this at Hamcation. I had a much abbreviated presentation at Hamcation. This is a much longer, more detailed one. So if you left Hamcation wanting more information, well, you came to the right place because we got more info for you here. Okay, let's get started. So what is a Tangerine SDR radio? You might have heard the word, but this will give you a more detailed description of exactly what's involved. And the idea is we were approached in 2018 by the ham sci community, and these guys are a bunch of scientists who are smart guys, but they're not radio engineers. So they approached us at the Digital Communications Conference for some help building a radio that will allow them to analyze atmospheric phenomenon, ionospheric phenomenon, and space weather from a ground-based perspective. So on not a satellite or anything like that, just a ground-based measurements. So we said, well, that's great. We'd love to do that, but we'd like to build a more general radio that has numerous use cases, because we think we could maybe sell more of these and therefore get the cost down and provide a more ubiquitous radio, if you will. And I think the target was kind of like the red pitaya, but there were some things that they didn't do right. In fact, we started out actually at the beginning thinking, well, we'll just go find a radio. We'll find an SDR and we'll make a few mods to it. We'll maybe add some software, some firmware, and then we'll satisfy the scientists' needs with an off-the-shelf radio. Well, we looked and we looked and we looked, and we really couldn't find anything that met all the requirements that we wanted, that they wanted. So we thought, well, okay, let's spin our own. So these are the basic requirements we came up with. And like I said, multiple use cases, and I'll get to that in a minute here, of what we came up with. Also, we wanted to make the cost as low as possible to allow low cost entry based versus high performance. So we got trade-offs there that everyone has to take, which is pretty much what all the radios we looked at had to take, and we didn't like the trade-offs they took. So the shortcuts they took in order for it to not cost $2,000 and be out of the price range of the average experimenter, or have so few features, it'll be inexpensive, but have so few features as to not be very useful. We do want to make it all open source. So open source hardware, open source software, firmware, everything. So contribute to other projects that might be based upon ours, as we are basing ours on some of the projects that came before us. And of course, advances the state of the radio art, which is kind of like what Tapper is all about. So how do we do this? Well, this is some more features, but I'm kind of drilling down now into more detail. The key one here is, I don't know if you can see my cursor, but it's modular was the approach that we came up with. And modularity allows us to pick the features, allows you as the user to pick the features that you want to pay for, and don't pick the features that you don't want to pay for. Because some of the performance features can get expensive. And if you don't want that feature, then we don't think that you should have to pay for it. And that by doing it that way, we open it up to a wider bunch of use cases, a wider market. So reasonably small footprint, reasonably low power. Again, these are reasonably is the key word. So you have to do a trade-off on what does reasonably mean. I mean, is a 50-watt receiver in your budget? Probably not. But how about a 50-watt transmitter? Well, maybe you'd like that. So you have to do the trade-offs here. And a web-based user interface was really one of the targets, kind of like the Kiwi SDR, if you're familiar with that. The idea being that I don't have to load any special software. Every computer, even your phone, has a web browser on it. So if you get a web-based user interface, it becomes very easy to configure. And it's got to have a local display. I put that in there because it's an option, because part of the thing that we're trying to target too is a server-based system, whereas you would have your radio in the wiring closet and it would serve up data on your network, and then any computer in your house would be the receiver, if you will, and or transmitter, source of data or destination of data. And one of the things that the scientists wanted is they wanted to be able to capture data and then store it on a big cloud-based system. And of course, they started out with wanting DC to daylight, 24-hour storage, and so we added up how much data that would actually be. And then we explained to them that you're going to need something like 20 terabytes per day of storage. All of a sudden, because of course we put the data storage on them. And it's like when reality hits, you find out that, well, maybe we don't really need to store 100 kilohertz to 30 megahertz continuous data for 24 hours. And so we came to a more reasonable conclusion, which I will show you here what we came up with. So other target applications besides personal space weather station would be, for instance, a satellite ground station for the new geostationary satellite that they're working on right now. Other academic uses, maybe a low-cost version to teach SDR and FPGA techniques to students at universities. Or if you're familiar with the HP SDR project, just build yourself a receiver or a transceiver, but more not a flex type radio, but more of an experimenters type radio is what we're trying to target, which you see from the next bullet item, experimenters. And of course, once you get all these, you end up with remote ham radio kind of for free because it's all remote controlled anyway. And I'm sure there are others that we haven't thought of yet, because once we put the features out there, there are going to be people that come up with strange ideas, stranger than even we can come up with, for applications for the radio. So one of the things we wanted to do also was, if you're going to put a personal space weather station up at your house, and you're going to hook some antennas up, and you're going to measure the ionosphere, and you're going to look for solar storms, you might want to look for lightning, you might want to look for other kind of disturbances. Well, maybe you want to do some ham radio stuff too, because you are a ham operator. So we could build some of these features in for you for free that would just be included with the station. And I'll show you in a little bit how you could actually use the personal space weather station and your amateur radio features at the same time, seeing as how we have a software-defined radio with parallel processing and direct sampling front end. So again, should provide some amateur radio features, and we're going to show you that in a minute. Easy to use web interface, propagation information, i.e. like WhisperNet, reverse beacon network, built-in digital modes, because it is a digital system already, so it kind of falls out. Digital modes kind of fall out. And again, able to monitor the digital modes concurrently with personal space weather station monitoring. And SDRs can listen to multiple bands simultaneously, so you have a big advantage there over a conventional receiver or transceiver. And we have a special feature of email notification of heard stations. I'll get to that in a few minutes. So this will be a block diagram of what the personal space weather station would look like. This is what we're targeting as our first release. We're going to have a receiver only system. However, we've made provision for the additional features because we actually have 2 module locations for RF modules. So we're going to start out with a dual channel receive module, and then we have space for either another dual channel receive module if you want to do quad channel, and these are phase synchronous. So you can use these for diversity reception if you want. Or when we come up with the next board, which will be a transmitter board, you plug the transmitter board into the NU slot, then you have a transceiver. And we have a slot here for a clock module that you can put in a high performance GPS disciplined oscillator if you need that feature and you want to pay the money for it. Or you can put in a much more inexpensive oscillator, or we have a provision to put in no additional oscillator. If the oscillator requirements are not stringent, then you don't even need to have a clock module. And one of the features of the Tangerine system is the use of a client computer. Typically, a Raspberry Pi could be a single board computer, or if you need more computing power, you can use, what are they up to now? 16 core i9s, 12 cores or 16 cores or even more. And the reason we did it that way was because everybody says, well, you got an FPGA on the board. Why don't you put an FPGA with a processor on it instead? And I thought about that, and then you start thinking, well, okay, the processor I'm going to get on the FPGA is going to be about a gigahertz ARM core. It's going to be roughly equivalent to like maybe a Raspberry Pi 2 or an older version. And that adds over $100 to the cost of the data engine to change that part to include a processor alongside of the FPGA fabric. Well, I can buy a Raspberry Pi for $35. I can buy an Odroid N2 for about $60. And every year, new ones come out, and they're better and faster and cheaper. So we thought, well, let's just use a gigabit Ethernet link, and let's just use an off-the-shelf single board computer that are getting better and better and cheaper and faster, and it'll keep this more stable, and we'll put the things in the FPGA that need to go in the FPGA, and the things that can go on the single board computer will go on the single board computer. And I'll show you how this is going to work here. So what are we actually going to build now? We've talked a lot about modularity and features and all that, but we have to get down to some real hardware facts. So again, this is the basic block diagram. The key here is the splitting the single board computer out away from our radio. So really the Tangerine system, it consists of the single board computer and what we call the data engine. The data engine is the motherboard, if you will, that contains the modules that we were talking about earlier. And you can see we have 2 RF module slots, we have a clock module slot, and we've added is a 3-port gigabit Ethernet switch instead of just a single port. One of the ports goes out to the FPGA. Instead of having a 2-port one, which is typical, you'd have to have an external switch to connect up the single board computer. So we put the 3-port switch on the board so that you can connect the single board computer directly to the data engine, and then you still have another port out here to connect to your local network, your home network. And over this link here, the single board computer will control the data engine. And over this link here, the data engine will output UDP streams of data. And I say streams because there's going to be multiple ones. You'll be able to target different destinations, which means you can hook up multiple I call them receivers, but they're a single board computer with a monitor. That's your receiver. And you can put as many of them as you want, as many as we can support the streams in the FPGA. So what happens is each separate virtual receiver, these are hardware receivers out here, they will link to a virtual receiver in the FPGA, and each will get its own stream of data, and it will act like an independent receiver, and you won't even know the other receivers are there. You get your own separate stream of data. And the streams of data can be directed anywhere. They're just UDP packets. So they're under control, source and destination are under control of the single board computer, which directs all the traffic here. And by doing it this way, it alleviates a lot of the security problems, because now security is handled by the single board computer, and I don't have to worry nearly as much about getting the data engine hacked or getting it, bad things happening, because the outside world talks to the single board computer. And since we will run Linux typically on that, we get all the advantages of having a Linux system. Okay, so my theory, get ready for the details coming up, because it's going to be fun to see what we came up with. Okay, so again, the block diagram here, we'll start with the red box. I'm going to discuss this part right here, the FPGA and the 3-port gigabit switch. And for those of you who don't know what an FPGA is, I think everybody does by now, but just in case, it's a field programmable gate array, and it is basically a sea of hardware gates that is programmable to become any configuration that you can program it to. So the FPGA manufacturer provides you with a compiler, which is similar to a software compiler, except what it does is allows you to use a hardware description language such as Verilog or VHDL and describe the hardware components that you want. And the compiler will then combine the gates and flip-flops into the blocks that you specify, and it will interconnect them the way you want them to be connected. So when in a microprocessor or a computer, I specified a series of instructions that the processor has to execute serially in time. In an FPGA, you actually specify the hardware that it will be generated in parallel all at once, and then it will operate in parallel. So it's kind of like designing your own PC board in software. It's, at any rate, so we have an FPGA that we can define the hardware features of, and then we connect that to a hardware gigabit East switch. And the FPGA we're using is a Max 10. It's the largest one. This 50 stands for 50,000 logic elements. And it's in a 672-pin fine-pitch BGA. So this will not be a kit that you can assemble at home. This will have to be professionally assembled. But it'll be worth it because the features of the capability of this part is tremendous. We also added some DRAM. Some QSPI is quad SPI, so it actually reads the data out in 4 bits at a time, even though it's organized as in bytes. Then we also have a smaller serial EEPROM, and you might ask the reason that these were chosen. Well, they're chosen because, first of all, they're inexpensive, and per bit, the memory is cheap per bit. And these are also, these are also standard parts that are available on development boards. So it makes the development much easier because you could just copy the way they're connected up, and if there's any FPGA code that you need to talk to these parts, which for the DRAM there is, it's a DRAM controller, you can get an example from Altera, which is now Intel. You can get an example off of their webpage. So you can get, it's like getting a driver for free. And then we have a micro SD card, and this will likely be used for either upgrading or for storing IQ data. Okay, the power supply is going to be, it's going to take a single 12-volt input from your station supply. No funny voltages. We already mentioned the 3-port gigabit E switch. We also have a cryptographic chip on there, which will store a 72-bit unique serial number, which means that every radio will be able to be identified, which I'm not sure how we're going to use that, but I got this. And you'll see a lot of these features are borrowed from the other SDR radios and some from each radio. The Lime SDRs have this part on there for some particular reason. It also allows you, if you're doing any cryptographic, any encryption or decryption, it allows you to store the keys on the board in this part. Doesn't actually do the encryption for you, but it allows you to store the keys. And then temperature sensors and a power on reset monitor, a fan header. These are just generic things that pretty much every board should have. So moving on to the RF modules, this is really the heart of the radio because the RF modules are going to define the performance of the radio. So you're going to get 2 slots, identical slots of 140 pin connectors, and we've arranged the slots in a parallel fashion such that we could actually build a double wide RF module that would use both connectors and give us much more IO if perhaps we needed that. So that's something that'll be coming in the future if we need it. And you'll find a lot of this. Part of the reason that this has taken so long is it was originally conceived in 2018. This has morphed a lot from the original concept to what we have now, because we've gone around and around and had lots of discussions on what features are useful and what aren't and what could we do. And one of these is line up the connectors so that you can use both of them on one board. And may never use that, but it's a possibility is there anyway. So the first board we're going to make, this is the first RF module we're going to make to go with the data engine, is a 14-bit 122 megasample per second ADC, and it's a dual, so that gives us 2 channels, synchronous channels. We'll have 2 attenuators, which are remotely switchable, and a 20 dB LNA. And remember, there's 2 LNAs because there's 2 channels. And fixed 55 megahertz low-pass filters. These will be removable if you want to do undersampling. And the interesting thing is you can just remove this filter, and then you can use the optional user-defined plugin filter. We provided headers for a TBD future module that you can design if you say, oh, I'm really interested in only 14 to 15 megahertz. You could build a bandpass filter and plug that in. You could build a preamp for 6 meters and plug it on. You could build whatever you like on these plug-in filter modules. So we have a spec for the module, and then you can go ahead and design one you want. Also, we're going to have an onboard 50 ohm calibrated noise source so that you can, I guess it's mostly going to be used for checking if your system is operating properly, but it will be really, this is the request of the Personal Space Weather Station guys. We want to make sure all of the cloud collected data comes from calibrated sources so that they can be compared A to B. And made a special effort to keep the power supplies on board. Lots of linear low noise supplies, because switchers are kind of like contradictory to the process of getting a very, very sensitive receiver and putting it in a box alongside a switching power supply. You're going to hear the switching power supply. So at any rate, we made a special effort to filter the power supplies. And the antenna connectors come directly off the RF modules. They don't go back through the data engine. And I'll show you how they physically connect up here in a minute. So this is the block diagram of the first RX module. And remember, this is the first one. These are modules. So there's going to be a lot of these, in my opinion. There's going to be high performance ones. There's going to be cheap ones. There's going to be throw the kitchen sink at it ones. There's going to be transceiver ones, VHF ones, whatever people can come up with. The idea is we want to publish the spec, so you guys out there who are like microwave guys can build me a 6 gigahertz version. In fact, one of the ones that is coming up, I'm not going to touch on it today, but one of the guys in our Monday night Zoom group is interested in lightning detection. So he wants to build a 10 kilohertz to 200 kilohertz receiver, a VLF module. So we're giving him all the specifications of the connectors and the physical placement of them. He's going to actually be the first non-original board. So the first board set's going to come out from Tapper, but he's going to have another board that's going to be VLF receiver that's going to plug into the Tangerine. And it probably won't be too much later than our initial offering, because he's working on it right now in parallel with us. So you can see how we switch in the noise source, and we have the attenuators and the filter option. And again, this is removable. The LPF's removable and bypassable if you want to do that. And the 20 dB amplifier is always in circuit. So basically, if you don't want the gain there, you switch attenuators on. Okay, so future modules, maybe a space module for the Phase 4 ground system for satellites. There are lots of new ICs coming on the market that are RF subsystems, like the Analog Devices 9361. There's a whole family of those, which are actually integrated transceivers, and they cover 70 megahertz to 6 gigahertz. So putting one of those on a board and making it into a module would be an interesting project. Lime also has some similar modules from varying frequency ranges and varying performance. So any of these could be placed on a module and then plugged into the same data engine, the same hardware that you already have paid money for. So, and I want to especially thank Tom McDermott, N5EG, for he actually designed the RF module. So he's a highly skilled RF guy. So thank you, Tom. Okay, on now to the clock module. And the clock module might be the most optional one of all the modules, because you can actually operate the board without it. But the performance of the jitter and the frequency accuracy is not particularly good. The oscillators that are on the data engine are meant to be inexpensive and good enough for a receiver. But if you want a lab instrument or you want a personal space weather station, they're not good enough. So we have the optional clock module that you can add, which will improve the performance of the clocking on the data engine. So like I said, you don't have to have a clock module if you don't want it. If you don't want to pay for it, if just a regular receiver is good enough for you, or you're experimenting. And so if you don't buy it now, buy it tomorrow. Christmas comes at least once a year. So the first one we're going to come out with is a synthesized DO. We call it Synthdo, which is a disciplined oscillator. So it's a GPS disciplined oscillator with a reasonably good TCXO on it, and some additional circuitry to square up the TCXO and stabilize it, and then a high performance synthesizer to provide us with all of the different clock outputs, different frequency outputs that we may need for the various circuits on the data engine. And the idea is to lay the board out with 3 different GPS options, and you can see the cost difference is phenomenal here. Not so much between the bottom 2, but between the top one and the middle one, that'll double the cost of the module easily. So you have to really need this to want to pay that kind of money for it. So we're going to make an option available to have either one or both of these lower cost modules at the expense of performance. You won't get the performance that you get out of the expensive one, the F9T, but you pay for the performance you want and that you need. The thing about the F9T is it does some things for the scientists, like it's a dual band GPS, which allows you to measure the total electron content of the ionosphere. So what they do is they measure the characteristics of the signals coming from the satellite, and since the satellites are on different bands, you can actually figure out what the electron content of the ionosphere is that these signals are passing through, because these satellites are outside the ionosphere. So all of the signals that we get from satellites have to pass through that layer. So all of those layers. So anyway, it gives the scientists something to measure. So this is what's driving this one right here. And this is it just came out within the last 6 months, so it's pretty new. And one of the other interesting things is we're going to be able to do is take the clock module and mount it on an interface board and create a piece of laboratory equipment just for you, just for your shack. So if you're a time nut, or you like high accuracy clocks or low jitter clocks, you can take the features of this clock module and convert it into a piece of test equipment or lab equipment that resides in your shack. So this is the first design of the clock module that we came up with. And you can see it looks, but first thing I see is expense right here, because it's got a small FPGA in the middle to do some signal processing, but it's got a DAC and a VCXO, actually, because you got to be able to correct the frequency here. It also has a synthesizer. And I mean, it's very nice, but it looks complicated. So this is actually the one we're going to build, because John Ackerman, N8UR, has come up with the theory that this gets us about 90% of the way there that this does. But this is fantastically cheaper. And as long as you're still using the more expensive GPS, you get pretty darn close performance to what we could achieve with the other one, and with a lot less effort and a lot less cost. So this is a graph of Allen deviation. This is frequency stability over time, basically. And the way it works generally is that for very low, close-in time periods, like under a second, the oscillator's characteristic is what determines this value here. And then as you average over longer and longer time, the GPS's contribution is dominant. So in this region right here, between 1 second and 10 seconds, is typically where the crossover happens, where the local oscillator becomes less dominant and the GPS becomes more dominant. So if you were to continue the GPS graphs, you'd see that they go way up high, which is undesirable. Lower is better. So you want to use the oscillator's characteristics to get close in deviation, and use the use the GPS for long term. Anyway, so this line right here is pretty much our goal. And you see we don't quite make it at the very low, very quick close in times. But by the time you get out to a minute or two, you get pretty good stability here. This is the green one is the F9T, and you can kind of see, big dollars, medium dollars, cheap dollars. It kind of just flows. Okay. So I want to also thank John Ackerman for taking on the clock module design. He's the time nut that is very into the time. He has multiple rubidium standards in his basement, and I told him, a ham that has one clock knows what time it is, but when you have two clocks, you're never quite sure. So then I think he came back and said he's looking at a third one. So I don't know what that means, but I think it means he needs some help. But if you've ever been to his lab, it's very impressive. Okay, so back to the hardware. I want to show a few of the data paths here. The green is the high-speed data paths, and the orange is the low-speed data path. So what we've done is we've taken, and I'll start on the right-hand side here, and you're probably all familiar with Raspberry Pi hats. Well, we've designed the connector on the board to be compatible with the Raspberry Pi hat, but the Raspberry Pi hat to me is not quite good enough because there's no high-speed I/O. So what we've done is we've added another connector, excuse me, for higher speed I/O, and I'll get to this in a minute. I'll show you what the physical topology is, how we did this. But the idea is now we call it a leaf board because you got to have catchy names, right? So we call it a leaf board, and it's really a Raspberry Pi hat with an extension connector on it that gives you the high speed I/O. And it also gives you some additional power that you don't get off of the Raspberry Pi hat. So this enables us to build more interesting boards. I believe that the VLF module is going to be a leaf. It's going to plug on here, which is interesting because then that means you can use a VLF module alongside our regular receive module and have full coverage from 10 kilohertz up to about 60 megahertz with two different RF modules. And then we have the Gigabit E port I told you about is the 3-port unit. So there's 2 ports here and 1 back to the internal data engine. This is a full gigabit Ethernet port. And it's a switch, however, so you really have 1 gigabit of data shared amongst the 3 IOs, if you will, the three ports. But that's okay because the data engine is the centric port here, so it's either going to be talking to the single board computer or to the network outside, or keeping its mouth shut and letting the Gigabit Ethernet just run right through here and stream data out to your local network. We have also added a USB 3 port. It's a true USB 3. It's a single line, 5 gigabits per second bidirectional full duplex port, similar to what the I think the Lime SDR Mini uses this part, same part. It's an FTDI 601 part, and don't really have a current use for this except it is an additional high-speed port, and it's actually higher speed than the Gigabit Ethernet. So you could, in fact, do some external processing via USB and still be network connected with the Gigabit port. And then down on the bottom are the 2 RF modules. This is something that was deleted, so I didn't have a chance to take it off the drawing. But here's the 2 RF modules that actually provide the interface to the real RF world outside. And then this is a low-speed connection. This is actually is meant to be on the same header as your Raspberry Pi hat, but you can connect that with serial lines or I2C ports or UARTs or GPIO if you want to talk to the single board computer, because most of these guys have an IO header comparable to what ours is. We haven't really made it so you can plug a Raspberry Pi PC computer onto our board, because our board is supposed to substitute for the Raspberry Pi computer. But the idea is you can use standard Raspberry Pi hats on the data engine. Okay, I talked a little bit about these already. 5 gigabit per second. And we also have a USB 2 interface, which I don't think did I show that on here? I did not. But somebody was, while we were having our discussion, somebody suggested, well, you know, you've got these RTL dongles that are everywhere for 20 bucks. Why don't you put a USB 2 interface on? It won't cost you that much, and that will allow you to plug an RTL dongle onto the data engine, and then you can do a lot more processing on the data coming from the dongle than you could like if you just plugged it into a regular USB port of a PC or a Raspberry Pi. And then you could also feed the data on out the USB 3 port or out the Ethernet port onto a host computer or Raspberry Pi or whatever you want to, whatever your computer is. But it's designed really for a DVB dongle. And oh, and by the way, since it's a host interface, you'll be able to plug your thumb drives and your memory and all that on there as well. And then I already mentioned the RJ45 ports. So the aggregate is 100 megabytes per second or a gigabit. But it is a switch, so you're limited to the aggregate of 1 gig. Okay, now let me talk a little bit about the I/O that we're going to do here. The idea is for the I/O is for sensor and shield interfaces, and we have, like I mentioned before, we have the dual connectors, a high-speed one and a low-speed one. The low-speed one closely matches the standard Raspberry Pi hat, and the high-speed one is actually it's an M.2 connector, which is the same kind of connector that they use now for solid-state drives. But the reason we're using it is not because it's for solid-state drives, but because it's a very inexpensive connector and it also handles high-speed data very well. But this would be where you put connectors for a PTT, a keyer paddle, a PA key, and all that. We deliberately left these off of the main board because they add costs for people who may not want them. Again, modularity is the key. And we could build a Raspberry Pi hat that has just a few connectors on it for, you know, $10. So if you need that I/O, then you can get that through the Pi interface. So how we make the leaf, a Pi into a leaf, so to speak. The blue outline here is the size of a Raspberry Pi hat, the specified size with the 40-pin female connector here on the hat. The male connector is on the Raspberry Pi board itself. Our connector will be a male connector duplicating the Raspberry Pi functions, but we are going to extend the size of our board, and this is going to be a gold finger tab that looks like a solid state drive that fits into the M.2 connector on the data engine. So what you'll do then is you'll slide this downward into the connector, and then you'll tilt the board back and engage the Raspberry Pi connector up here. So this will actually be the physical stabilization for this connector, because as you know, those M.2 connectors, they're like DRAM sticks. You stick them in at an angle, and then you tilt them down to make contact, and you either have to tie them down with a screw or some kind of standoff or some other mechanical way to keep the thing captive, because the M.2 connectors don't do that themselves. So what could you do with that? Well, you could use Raspberry Pi hats and just plug them on. Or you could make custom boards like Jonathan's going to do with the VLF board to take advantage of the external connector, the high-speed connector. Or what you can do is, if you're into Arduinos or Beagle boards, click modules, PMOD, alternate, all these other connectors down here are other manufacturers' low-speed I/O. So you can build a Leaf board or Raspberry Pi, but they already have Raspberry Pi headers that do their hats that do this, that have Arduino Shield connectors on them, or they accept PMODs or click modules. These are all modules that you can get. And click modules is a European thing. I'd never even heard of it before about a year ago, but there are literally, there's over 500 different click module types. And they're little bitty things. They're, you know, like a postage stamp size, but they'll have sensors, they'll have low-speed I/O, they have switches, they'll have little OLED displays. I mean, you can get almost anything you want on these modules. So if we wanted a set of those, then we could build a Leaf board that will accommodate those. So what we talk about for future Tangerine SDR data engine boards, since it's modular, we can put maybe a larger, faster FPGA on it and substitute it for the board that you already have. We could add more RAM. We could put an SSD on it maybe. Or one of the reasons for using gigabit Ethernet is that gigabit Ethernet scales very nicely to 10 gig E, 40 gig E, etc. So in hardware, so we could end up with another higher performance board that has more logic gates in the FPGA, a larger FPGA, or more RAM, or more solid state storage, but it will still use the same RF module and clock modules that you already have. So we'll see how that goes, because that's the plan now, is once we get the first set of boards done, then we'll look to see what are the shortcomings. In other words, do we run out of FPGA? Do we run out of communications bandwidth? Do we need more RAM? what are we short on? What didn't we pick correctly? And then we'll fix that and come out with a newer enhanced board at some point. So this is kind of the way it all plugs together. This is kind of a hard to understand, I guess, in 2 dimensions. But if you can see, the black outline is the baseboard, which is the data engine, and it has finger connectors down here on the bottom, gold fingers. It has the M2 and Raspberry Pi connector up here in the upper left for the leaf board, and it has another M2 connector here for the clock module, which goes along the lower right-hand side. So it ends up with the data engine in the middle. The 2 RF modules are in blue. They're underneath. They're on the back side. You can see how they stick out at the top with their SMAs, but the data portion of them plugs in at the bottom. So they're the full height of the data engine, but half the width. So you end up with 2 slots on the back, then the data engine, and then on the top of the data engine, you have 2 non-overlapping slots, if you will, one for the clock module in the lower right, one for the leaf in the upper left. So you end up basically with a 3-board stack. Even though the top boards, there's 2 of them, it's still the clock module and the leaf are on the same Z-axis height. So it ends up a 3-board stack. So where are we now in the project? The RF modules is the one that's the furthest ahead. The schematic and the BOM are complete. The PCB layout and design are complete. And we're just basically waiting to confirm that everything will fit together, because the way we do it is we design the 3 boards, the clock module, the DE, and the RF modules, and then we take the computer generated models of the boards and we verify that in the CAD system they will plug together and not interfere. The connectors will fit, and also we want to make sure that the connector IO is on the same pins. I mean, we have to double check that, but the point is that we got to do some system integration before we run off and build anything. So the RF board is kind of in the wings waiting. It'll be the first one out, but again, it won't be useful without the data engine, so we better make sure they play well together. But it's ready for prototype building. The data engine, the schematic and BOM are complete. It's actually in PCB layout design now. I'm looking forward to getting a preliminary placement next week sometime, and then we can begin the checking to make sure that the RF modules will fit onto the back of the data engine. The clock module is John has done a lot of work testing the proof of concepts for the clock modules using the development board. So we'd use off-the-shelf development boards that have the chip on it that we want to use to verify that we can get the performance that we want by putting that chip on our board. But we can go buy the development board right today, so we don't actually have to build anything custom to determine what our performance is going to be. But again, you saw how much the clock module was simplified by thinking about it and talking back and forth and brainstorming and coming up with simplifications that looked like they would work. And it's way simpler than it was to start with. So we're really happy about that. And the schematic is about 80% complete. All the parts have been chosen already. We're still working on putting the schematic finality together. And then that will go in and we'll get a placement for that. And then we'll verify that we've got the right size and connector placement so that all 3 of the boards plug together. And then once we do that, then we'll finish up the routing on the data engine and the clock module, and then we'll be building prototypes. And when can I get one? Well, prototypes, we're thinking it was supposed to be by Hamvention, but since Hamvention is canceled this year, the date still happens, so we still could try to meet that date. And then production sometime toward the end of the summer, beginning of the fall is what we're looking at. And we don't really have any pricing yet. We're trying to keep the basic system significantly under 500. I'm not sure how close we're going to get to that. Prices have been varying all over, so we'll see. We'll build it as cheaply as we can. Our webpage, tangerinesdr.com, pretty easy to remember. There's lots of documents up there. There's specs up there. There's links to follow. There's videos to watch. Very KV0S has done a great job in keeping this all together. And we have an email listserv. And again, this is more for reference because I guess these are going to be up on YouTube, so you'll be able to check this. And again, everyone's welcome. Sign up, keep your ear to the ground, watch what's going on. Even if you don't want to contribute, you don't have to. But if you want to keep abreast of what's going on, you're welcome to subscribe. And every Monday night, we have a Zoom session at 9 p.m. Let's see if I get it right. It's 9 p.m. Eastern time. And again, all this information is up on the Tangerine SDR.com webpage. But we have a weekly Zoom session. Link's always the same. So feel free to join us and just see what's going on. You don't have to speak. You don't even have to turn your video on if you don't want, but we would like to see you and talk to you and welcome you. So that ends my presentation. I thank you very much. I guess we turn it back over to Daryl now, right? For Q&A.
Yes, sir. I have a question. I'll start off first. I presume this is going to be a kit through Tapper first. It's going to be a kit form. Is that right? And do you have any plans to produce a finished, fully assembled version?
Okay, there will not be a kit board. There will be boards. So you can buy a board and combine the boards together any way you want. And eventually there'll be multiple versions of each board, each clock module, RF module, and data engine. But the complexity of the assembly and the type of ICs we have to use to get the performance we need does not lend itself to making it a kit, because the average ham just can't solder a 672-pin BGA. I know I'm maybe a little bit above average in SMT rework, and I can't do it. So I won't say that you can't. I'm sure someone out there will call me on it and say, well, I can do it. But yeah, okay, maybe you can, but it's a very unique and highly skilled operation. So we're going to provide the boards fully assembled, and the advantage you get of that is we test them too. And it turns out that you actually end up getting, through Tapper, you could end up buying the assembled and tested board cheaper than you can buy the blank board and all the parts. So you're still better off getting an assembled tested version. And then there is, yes, a plan to come out with a radio, which includes everything in a box. And because I know the next question someone's going to ask me is, well, do you have an enclosure for it? Well, not yet, but we're planning to.
So in other words, just to reiterate, you'll be able to buy the fully assembled boards, because I could do low quad flat packs and quad flat with no leads, but BGA, I think that's a little beyond my ability. Yeah, certainly.
And you may want to do some minor modifications to the board. That's up to you. And because there are a few things, like on the RF modules, we actually have a choice of which clock source you're going to pick based upon whether you want to use the onboard clock on the data engine or the high performance clock module. And what we do is we deliberately make those surface mount parts like 0805s, big parts that the average guy can see, you can do with a reasonably simple SMT rework station. And we encourage you to do that. And we help you by making those parts a little bit bigger. But in general, we don't encourage you to be soldering the 0402 parts or the BGAs, because we'd like you to succeed, and it's hard. I mean, there's no doubt about it.
Even with a 50 times webcam, that'd be hard. And I think I've done parts that small, and it was a 3.3 volt regulator, and it was on the RXTX Ensemble. That was the first surface mount part I ever did, and I got it right, but boy, it was tricky. So you can buy this. You can buy the fully built boards, tested, and assemble them in a case yourself, or you could buy eventually the fully assembled radio product then.
Right. And my American Beauty is too big to solder these SMT parts. Remember the American Beauty kilowatt iron that's like about that long with a chisel tip the size of your thumb?
250 watt iron for surface mount. That'd be quite an interesting experiment. Right. So anybody, you could go ahead and raise your hands in the reactions thing if you have a question. you're still muted, but you may unmute yourself and or ask that way or post in the chat. And by the way, this presentation and all the others is on the section website at the TECHCON page. It is listed there for your convenience. So questions? I'm going to give a thumbs up too.
I knew I could dazzle everyone with details.
Yeah, it sort of reminds me of what my dad used to say. I like that expression. You know, if you can't baffle them with baloney, dazzle them with detail. That's pretty good. I like that. So, okay, any questions? One last call. And all right, well, Scotty, thank you very much for bringing the presentation. Definitely plan to come back to the TECHCON next year. And who knows, maybe if there's enough interest, we may have a special thing on Zoom meeting sometime down the road for folks. We get 2 or 3 that want to buy the things and put the boards together in their own enclosure or whatever. We may do that in the road if there's enough interest.
Well, and also if the DCC follows through this fall in Charlotte, North Carolina, and we actually have an in-person one, you'll be able to come up there, and it's not too far from you. You'll be able to come up there and see the real boards, because if we don't have them by then, they're probably going to have to fire me and cut my pay back to 0. Oh, wait, it's already 0. Well, anyway, they have to cut my pay off.
Yeah, like I said, the division by 0 is undetermined. So that's uncharted territory.
Yeah, really.
Okay. All right, well, if there's no further questions, we're going to end the YouTube stream for this presentation, so it will be complete. And one last call for questions. All right, well, thank you very much, Scotty. And you can hit the applause button, being that we won't all hear it anyway. So,
all right, thank you, Daryl.
All right, Scotty.